Hey, good morning. All right, we are back again, starting a new unit, unit 4 now. And we start off with quite a quite a day of notes here. So I promise it's gonna start a little slow. You're gonna wonder what we're doing for a few minutes here, but we're gonna tie it all together by the end. So a new unit today, unit 4. We're looking at electrons. So for the last several chapters, we've worked with protons and neutrons and the nucleus of the atom. And now we're finally getting to electrons. And we'll start today, 4.1, with what we call the electromagnetic spectrum and orbitals. The electromagnetic spectrum and orbitals. So just so we're all okay, spectrum, see this word a few times. It means it's kind of like the opposite of grouping. So think of height. Think of the height of people. If we lined up everybody in the classroom from tallest to shortest, we wouldn't just have two groups of people. It's not like we have short people and tall people. No, there's a kind of continuous spectrum all the way. There's someone who's the shortest person, then someone slightly taller, and slightly taller than that, and slightly taller than that, and so on and so forth, all the way to the tallest person. There's going to be slightly shorter than them. So that's a spectrum, just one increment, small little tiny increments all the way, and we don't really have groups. So turn the page sideways here. I'm going to use a lot of room on this part. So this is what's called the EM spectrum. EM stands for electromagnetic. We're usually going to just call it the EM spectrum, but I wanted you guys to see it. All written out, so we did that. So electromagnetic, usually called the EM spectrum. We're going to start up here at the tall. Again, like I said, kind of the tallest of people will be up here at the top. Let's keep knocking the camera there. Sorry about that. And his wavelengths kind of look like this. Really, really long. So when I say long, I'm talking about the distance between peaks. So those are radio waves, and they have the longest wavelengths. Now we're not going to cover all of them. In fact, I'm going to kind of skip a few here. I'm going to come down to IR, which stands for infrared. It's like inferior to red. And the trick is to make it just a little bit shorter than that one. So when I say shorter, I mean that those peaks and valleys happen just a little bit earlier. So you see how this one peaks and then it goes down. This one went down just a little bit past where this one went down, and then this one's peaking again. This one didn't peak till later. So this wavelength is just a little bit shorter. All right, now comes the biggest part of it. Well, it's actually the smallest part. It's a really small little area here, but it's the most important part to us, the visible light spectrum. So these are the colors that we see. Again, these are really very small. It's not a very wide range visible light. So we're going to blow it up so we can see all of them. So I'm going to blow up this area. So blow up this area. There's our visible light spectrum. Word light there, visible light. And we're going to bring back, hopefully you guys remember a little bit from your art classes over the years. And the colors of the rainbow, Roy G. Biv. So starting off with red, it has the longest wavelength of the visible light colors. And again, we're going to Roy, so red, orange. And orange's wavelength is just a little bit longer than red's. So again, his peaks happen just a little bit before red's, his valleys happen just a little bit before red's. It's offset by red, but just a little bit there. Next up, we're looking at Pam's first fiance, Roy. So Roy, R-O-Y. Hopefully it's showing up all right. Yellow is kind of a difficult color to color with. There's our yellow line. Again, it's really tough to see. You're just going to have to kind of trust me, it is there. Following yellow. Green. And you notice each of these colors gets just a little bit tighter, just a little bit closer, the peaks and the valleys, just a little bit closer than the one before it. It's because the wavelengths are getting just a little bit slower. So we got Roy, G, Biv. There's the B part of Biv. BIV, I is for indigo. Interesting. Not seeing a really good purple in here. Kind of weird. I don't know if you can see that or not. The picture of the crayon on the box here is purple, and yet there's no purple in the actual box. Very interesting. All right. Well, we will pretend this is purple, violet, I should say. And he's going to have the shortest wavelength of all of these visible light colors. All right, so there we go. Drawing our rainbow. There's the colors we see. And again, they're all associated. All these colors that we see are associated with a specific wavelength, with a specific length. IR, infrared, means like inferior to red. It's just outside of the range that we can interpret and we can see with our eyes. That's the IR spectrum. On the other end, we have the UV spectrum. So that's ultraviolet. It's just beyond violet. It's a little bit too short for us to see. We can only see up to violet. I'm not going to draw those waves. I think you guys get the picture. You know, those waves would be a little bit tighter than this one. We would then have X-rays, which are even shorter than UV. So when you go into the doctor's office and they X-ray your bones, that's what those would be. And finally, something that should look familiar from last chapter are gamma rays. And gamma rays are going to be down at the bottom. They have the shortest wavelength. So these guys, I will draw these guys. These guys just go back and forth really quick. So gamma rays are really tight together. Again, you can use your imagination for the X-rays. They're going to be just a little bit longer than these guys, but look pretty similar. And UV light, again, is going to be between violet and X-rays, just a little bit tighter than these guys, but not quite this tight. All right, so there are our waves. We're going to come back to this page throughout the next part of the notes. But there's a couple of notes in what we're looking at here. All of those waves, doesn't matter. Some of them look long, some of them look short, some of them look tiny. They all travel at the same speed. It's called the speed of light. Very famous speed. We symbolize it with the letter C. So C stands for the speed of light. It has a numeric value, of course it does. And that is in a vacuum, which we're always going to assume we're working in a vacuum in this chapter. 3.00 times 10 to the 8th meters per second. So that doesn't change. It's always a constant, and we can use that actually to figure out a couple of other things. So here's what we found out over the years. C is equal to this little weird little symbol here is lambda times nu. It looks like a V. I oftentimes call it a V, but it's really the Greek letter nu. So it's Greek letter lambda, Greek letter nu. Well, what are those symbols? Great question. Lambda stands for wavelength, which is the distance between two waves. So that's what lambda is. Turn back to this page. We'll take a look at our radio waves. So they always say just be consistent with where you measure. So if you wanted to measure from valley to valley, you could. From start of the way up to start of the way up, you could. I usually go from peak to peak, but there is one wavelength. And that's symbolized as lambda. So there's one wavelength. Pretty big. We go down to the bottom, and you can see our wavelength is much, much smaller. Tough time spelling this morning. So there's one wavelength down below, much, much smaller. Write the quick note here. Up at top, we have long wavelengths. Down at the bottom, short wavelengths. Long wavelengths at the top, short wavelengths at the bottom. Now these are measured in meters or some derivative of meters. So kilometers. Radio waves are sometimes kilometers long, or centimeters. I think IR waves can get up to be a centimeter long, or millimeters, or decimeters, or nanometers. You see nanometers a lot because that's actually what we measure visible light in, is in nanometers. So some derivative of meters, because wavelength is a distance between 2 points. The other letter there looks like a V. It's really Greek letter nu. This is our what we call frequency. And frequency is how many waves pass a certain point per second. So it's measured. It's kind of weird. We measure frequency, and we have kind of two options here. Now I have one I prefer, and it is not the hertz. So technically the term is called hertz, Hz. I'm not a big fan of hertz because it mathematically, I don't like it, it's just Hz. I prefer the per second. Waves per second. And we symbolize that as 1 over s, or s to the -1. So you guys are familiar with something to the -1 is the inverse. So these two things are saying the same thing. So mathematically, if we weren't aware of that, hopefully you now are. 1 over s, that's per second. You could use a per second in a lot of places. I know it sounds kind of weird, but how many meters per second? There's a per second. Just put meters on top. How many donuts can you eat per second? Well, it'd be a per second. Put donuts eaten on top. You could discuss how many dollars you make per second, and it's a way to kind of transfer into time. So that's the per second. It's kind of tough to draw time. How do I draw 1 second? Well, I don't have a great answer for you. Instead, I'm going to say this right here is 1 second. So the frequency of my radio waves is very, very low. I didn't get very many radio waves to pass this point. And once I got like 1/10 of a radio wave. So the frequency is low frequency. Down at the bottom, however, we have a shorter wavelength. We can imagine we do that same 1 second, so that same kind of area we had up there, about the width of my finger. Well, man, we got a whole bunch of more waves down here, like 2 or 3 waves in there. So that's a much higher frequency. What do you call that? 2 waves in this one? Only a tenth of a wave. So this one has 20 times the frequency, a much, much higher frequency down below as compared with up top. So these two numbers work together, wavelength and frequency, to equal the speed of light. And this makes sense. If you think about it, let's say the speed of light is 100. It's not. It's 3.00 times 10 to the 8th, but that's a big number to think about. If this were 100, and this were 10, and this were 10, what happens if this goes up? Our wavelength gets longer. So we're starting at 10, 10, kind of in the middle. What happens if our wavelength gets longer? The frequency would have to go down. So as your wavelength gets longer, your frequency gets higher. And again, hopefully you're kind of seeing that. You've got a short frequency, short wavelength, high frequency. Long wavelength, low frequency. So those two, as one goes up, the other goes down, and they always equal that value there, the speed of light. Hey, like I said, kind of throwing a bunch of random stuff at you right now. Probably feels that way. Wouldn't disagree. It probably does feel that way. But we will tie it all up and relate it back to chemistry by the end. So next up, we have another formula. So not only can we figure out the frequency and the wavelength based on the speed of light, we can also figure out the energy. So E stands for energy. It's measured in joules. And we'll use a little J to symbolize joules. H, haven't seen that one yet. H is what we say, or what we call Planck's constant. It's named after the man who discovered it, Max Planck. Planck's constant. So again, this is a number that doesn't change. It's always the same. And Planck's constant is equal to 6.63 times 10 to the negative 34th joule seconds. Kind of a made up unit there. We use this to make sure that everything else lines up. And frequency is our V again, our new. So we don't really need to take too many notes on that one. We just worked with frequency. We saw it up here. So given a wavelength of light, we can figure out the frequency. Once we get the frequency, we can figure out the energy of that light. Keeping all that in mind, we come back over here. Okay, think about that formula. What's going to happen? H is a constant. What's going to happen when V goes up? Will the energy go up? Will the energy goes down? If H is your constant, kind of think about that. Again, my trick, put in numbers you know how to work with. Let's call H 10. We'll call V 5. Okay, if H is 10 and V is 5, then E is 50. What happens if I bring V up to a 10? Now, so from 5 to 10, 10 times 10 is 100. Your energy goes up. So when your frequency goes up, your energy goes up. So back to this side, our low frequency, whoops, there we go. Our low frequency means a small amount of energy. Down at the bottom here, we got our high frequency. That means it's going to be high energy. Hey, one more question. I want to put fastest and slowest somewhere. Where should I put it? Top? Fastest? The bottom? Fastest. Where do you guys think I should put it? Think about that. I'm not going to put it anywhere. Hey, keep in mind all of these waves, low energy, high energy, doesn't matter. They're all traveling at the same speed, the speed of light. So keep that in mind. They all travel at the same speed. I know it kind of looks like this one might be traveling faster, but he's not. They're all traveling at the same speed, the speed of light. Not there yet, but I promise we're getting close to tying this all back to chemistry and explaining why we're talking about all of this physics stuff. All right, so this is not necessarily a new experiment. Scientists were doing this back, I think even Isaac Newton worked on this type of stuff. The light bulb might be new, relatively speaking, but mostly this idea, this concept has been around for a while. So scientists took a prism, which is a glass triangle, basically, and they shone white light through it. I'm symbolizing my white light is coming from a light bulb. And what they saw come out on the other side is that the glass prism actually ended up breaking up all the wavelengths of light. And again, exactly why this happens, pretty cool. Something you should go learn about in physics. Again, we'll get back to why this is important in chemistry in just a few minutes. You just have to hang with me for a minute or two here. My colored pencils in order. And our makeshift purple there, violet, okay. So again, this is not anything new. This is what's called a continuous spectrum. So you shine white light through a prism, all the colors of the rainbow come out on the other side, and you see a rainbow, a continuous spectrum. No gaps, no breaks, just from one color to the next, a spectrum. Again, this is nothing new. In fact, there's a really cool album cover artwork with this picture, basically this picture, a really cool picture from a really good British band. All right, well, this is a little bit newer. So this is around the roughly between the two world wars. Group of scientists decided, let's duplicate this. Search our light bulb again, or do the whole experiment again. I know you guys are having fun coloring. But this time, we are going to pass our white light before we enter it into the prism. We're going to pass it through an elemental gas cloud. So I'm not very good at writing with colored pencils here. So there's an elemental gas cloud. So what I mean by elemental is it can't just be air. Air has a lot of elements in it. Oxygen and mostly nitrogen, carbon dioxide. It's a combination of a lot of different elements. So what they did though is they got one pure element and they made sure it was in the gas phase. So oxygen, they got pure oxygen, ran the white light through the cloud and then through the prism. Or they got hydrogen, maybe that was the gas. In fact, they did it for a lot of different gases. And what they got is mostly a continuous spectrum, mostly. I'm not going to do orange. Skip down to yellow. In fact, for orange, I'm going to make kind of a black line. There's like a missing line there, a missing gap for orange. And then green. And I'm going to skip blue. Again, I'm going to have kind of a missing gap for blue. Indigo. And violet, or our makeshift violet. So there we go. So we got most of the colors came out. But there were these gaps, these missing colors, these lines that made it so it wasn't a continuous spectrum. Now, scientists being scientists, pretty smart guys, they figured this out. The element must have absorbed these particular wavelengths of light. So they called this an absorption spectrum. So you got most of the colors, but some of them definitely were absorbed. So this is our absorption spectrum. And again, being good scientists, we're like, well, must have gotten absorbed. Let's see what happens when we turn the light off. So one more time. I know you guys are loving all this drawing we're doing. So our light bulb. Now I'm not going to draw the lines around the light bulb. The light bulb is off. No light coming from the light bulb. Instead, I can imagine the gas cloud. It's been sitting next to the light bulb. It got kind of hot. It gathered some energy, absorbed energy from the light. And it is going to emit just a little bit of light. So it's going to cool. And as it cools, that energy comes off of it. And they passed that energy through the prism. And lo and behold, I bet you can guess what they got. They got the exact light that they were missing previously. And only the light that they were missing previously. Mostly, it was a black spectrum with no light. They didn't get the reds, they didn't get the yellows or the greens, it was all black. But they did get those missing orange and blue lights. And so the spectrum looked like this. Again, almost nothing there except the exact missing light from before. And that was kind of cool. Scientists were pretty amazed by this. Again, being smart people, they said, well, what must have happened here is that the gas cloud emitted those colors. So they called this an emission spectrum. So there's our emission spectrum. All right, we're getting really close to what this has to do with chemistry. Really smart people decided, hey, what's going on? Let's stop. Let's think about this. And here's what they came up with. We've got our nucleus in the middle of the atom. And surrounding the nucleus are energy levels on which the electron can exist. I'm drawing an atom here with 2 electrons. Now, when they shone their light at the element, so here's our element, we're looking at an individual atom of the element. When they shone their light at the element, most of the light went right through. And that's how we got this spectrum up here. Most of the light had nothing to do with the element. So it went right through and was not absorbed. And we got our absorption spectrum. But here's what they reasoned. Some of the light, in this case, the orange light, must have been absorbed by the electron. Why was it absorbed and why only that particular wavelength of light? Well, we've been talking about all day, those wavelengths not only have a frequency, but they also have an energy associated with them. So that orange light had the exact amount of energy needed for that electron to jump up to the next energy level. The electron absorbs that energy and jumps up from first to the second energy level. And again, why was it only the orange light? Because that's the exact amount of energy between these two energy levels. Down at the bottom, he also absorbed the blue light. Why blue? Well, if you guys remember, blue is a shorter wavelength than orange. That means it has more energy. Blue is a slightly more energy light than orange. Why more energy? Well, take a look at this electron. He's not just going up one level from the first to the second. This electron is going to go from the first all the way up to the third energy level. That's a bigger jump. That takes more energy, and that's why he absorbed the blue light. So up here in our absorption spectrum, we didn't see orange, we didn't see blue, because that energy was being absorbed by electrons jumping up into higher energy levels. Now, these electrons can't stay in the higher energy levels without the continued supply of light. So as the element is allowed to cool, they no longer have the energy to stay in these higher energy levels, and they're going to fall back to what we call their ground state, which is that lowest possible energy level. And when they do that, they release the exact amount of energy that they absorbed. The amount of energy that they used to get up there is released, and that's what we see on our emission spectrum. That element emitted this light, and only this light. And we don't see all those other lights. Those other lights aren't there. We just see that blue light because that's the amount of energy from electron down to the first energy level. We only see the orange light because that's the difference from electron down to from the second to the first. All right, so let's tie it all together. So here's our atoms. We brought back in chemistry. Let's pretend like this wavelength of light, because again, it's blue, we can measure it. Let's say that this wavelength of light we measured at 630 nanometers. Cool. Well, what scientists are able to, what we're able to, what you're going to be asked to do in your upcoming lab here is take this and convert it to an energy. Once you do that, you can figure out the energy between these energy levels. Really pretty cool stuff. How these scientists figured this out 100 years ago, I have no idea. So the first thing we need to do, we can't work in nanometers. If you remember the speed of light, it's in meters per second. Nanometers won't do it for us. So first thing we need to do is convert to meters. Nano is a pretty small number. There are 10 to the 9th meters in a nanometer. So our number of meters is 6.3 times 10 to the negative 7th meter. So it's a really pretty small wavelength. All right, first step here. C is equal to lambda mu. Now we have C, that's our speed of light, nothing new with that. What we want to do is we want to isolate our frequency. That's what we're first step here. In order to do that, we need to divide both sides by lambda. So here we go. Now we've got our V on the side by itself. So let's plug that. Let's plug that in. So we have our C, that's always the same. And we have our pencil kind of broken here. Sorry about that. So 3.00 times 10 to the 8th meters per second. And we have our lambda. (6.30 times 10 to the negative 7th meters. So our frequency, meters cancels out. We're going to be left with 1 over seconds per second. That's great. That's what we measure frequency in. But we need to actually perform this calculation real quick, not something I can do in my head, not easily at least. So 3.00. Second big E, get used to using that button, 8. Divided by 6.30, second big E, negative 7. I'm getting 4.7619. I'm going to underline that 19. Only 3 significant digits, only 3 significant digits. So the 4, the 7, and the 6 are 3 significant digits. I'm going to underline those last 2. And then times 10 to the 14th per seconds. Okay, so we've got our frequency. What are we going to do with this frequency is the next question. Well, our next formula, energy is equal to H times nu. H is Planck's constant. We have our nu. We don't need to rearrange anything. We're set and ready to go. I'm going to run out of page on my room. Man, sorry about this. This is sloppy, very sloppy. Sorry about this. I should have started a new page for the calculations. Trying to squeeze it all into one. Okay, so here's our H, 6.63 times 10 to the negative 34th joule seconds. And we're going to multiply that by the frequency V, this number here that we just got. So 4.7619 times 10 to the 14th. Sorry about that. It's going up the wrong side of the page here. Per seconds. Again, real sorry about that. This is just awfully sloppy. Here's Planck's constant, 6.63, big E, negative 34, times 4.7619, big E, 14. And there we go. Look at that. We just went 3 significant digits, only 3 there, only 3 there. I've underlined those, that 19. Seconds divided by per second, or multiplied by per second. So it's basically seconds divided by seconds, cancels out. We're left with just a joule. That's awesome. Oh yeah, we figured out how much energy is between this and this energy level. We figured that out just by seeing a wavelength of light. This electron emitted that amount of light. We can calculate the energy. Now we know the energy levels, or the energy between these levels of this atom, which is amazing stuff. I think that's out of this world crazy. I don't know if you guys agree on that, but I think it's really cool. Hopefully you guys see it and like it, and I think it's really out of the world cool too. Awesome stuff. I told you we'd tie it all together. It took a little while, but we did. So hopefully this helps. Hopefully you got your notes now, and we'll see you next time. We'll talk more about these energy levels. So long.